So, today's video is going to be all about inverse functions. Now, we've seen inverse functions before in the context of trigonometry. If you remember, for example, if you have that the sine of an angle alpha is equal to, let's say, 0.6, then to get the angle alpha out, what we did was we took the inverse function of sine, so inverse sine of sine of alpha is the inverse sine of 0.6, and these two cancelled each other out because this was the inverse function and this was the normal function. This just meant that alpha was equal to the inverse sine of 0.6, and then we put that in our calculators to find out what it was in degrees. And all inverse functions work in this way. This is just an example of an inverse function that we've seen before. And the important thing to note is this negative one here. You shouldn't think of this as a power. It's more just the inverse. So, this was just a little warm-up, a little example. Let's generalize this concept then for more functions. So, notes. The inverse of a function f of x is f to the minus 1 of x. And again, this isn't a power, it's just the inverse of f. And this inverse function reverses the action of the standard function, f of x. And that's all it does. So we've looked so far at functions where we have an input, then we put this input into our function machine, f of x, and this spits out a number, which is our output. And this always goes then in this direction. The inverse function takes us from the output and brings us back to the input. So this is f to the minus 1 of x. The inverse function of f says, how can I go this way? How can I take the output of the function and get back to the input of the function? So let's take an example. Let's choose a function f of x is equal to 3x, let's say. And we know that here we put in x, we apply the function to x, in this case we do 3 times it, and we get out 3 times the number that we put in. So the inverse function asks, how can we go back this way? Well, if to get from here to here we've multiplied by 3, then to get back this way we need to divide by 3. So in this case, our inverse function is x divided by 3. And in this case, x here is the output of the original function, and this is the input of the original function. So if I had here, let's say 2, then I apply 3 times 2 to it, and I get 6 out. The inverse function should take me back from 6 to 2, which I would get by putting 6 in to this function. So 6 becomes my input here. 6 divided by 3 gives me 2 as the output of this function, which of course is the input of the original function. So the question is that we need to ask ourselves always, from the output, how can we go back to x? How can we get back to the input? And in this example that we had up here, it was really obvious, because here we multiplied by 3, going backwards we just divide by 3. With other functions, it becomes a little bit more complicated. Let's say that this one up here was example 1. And this one here can be example 2. What about if we had f of x is equal to, let's say, 2x minus 9? To get from an input to an output here, I multiply by 2 and then take 9 away. How can I get back? Well, I'd need to first of all add 9 to the answer and then divide by 2. So if we had x as our input, 2x minus 9 is our function, and then our output would be whatever this evaluates to. So if I put, let's say, 6 in, I've got 2 times 6 minus 9, that's 12 minus 9, that gives me 3. How can I get back this way from 3 to 6? Well, there's a way of doing this every time. Your task is first of all to rearrange the original function to get x equals something. So if we have here f of x is equal to 2x minus 9, then I add 9. I get f of x plus 9 is 2x, and then I divide by 2, so I get f of x plus 9 over 2 is equal to x. And this here was my input of this function, and this here was my output. In the inverse function, we're just switching those around because we want to go from this output to this input. So now, replace f of x with x, because that'll be the input of our inverse function, and x with the inverse function notation, f to the minus 1 of x, because that will be the output, as we're going back to here, of our inverse function. So we have f to the minus 1 of x is equal to x plus 9 over 2. Then, as your third step, I would say, check it. Here we did an example where we put 6 in, and we got 3 out. With this one, I should be able to put 3 in and get 6 out. So let's say x is equal to 3. Is the inverse function of 3 6? If so, I've checked it for one possible set of inputs and outputs, and you can check it for as many as you like. You can put anything you like into here, get an output, put that output in here, and check that you get back to your original number that you've chosen. So if x is equal to 3, then f to the minus 1 of 3 is equal to 3 plus 9 over 2, which is 12 over 2, which is equal to 6. So yes, I've checked it once. This isn't a proof that it always works, but it's a good way of checking to see if we're on the right lines. Like I said before, I could have then chosen another set of values to check it again. So, functions f of x and g of x are inverses of one another if we apply f to g of x, we get back to x for all x in the domain of g. So there might be some x's we can't put in here, and we won't worry about those, but for all x's we can put in here, this should work. And g of f of x gets us back to x for all x in the domain of f this time. And actually, we can check that here. If we do, for example 2, f of f to the minus 1 of x is f of f to the minus 1 of x was x plus 9 divided by 2. And if I apply f to this, f was 2x minus 9. So I do 2 times this thing minus 9. These 2's all cancel. I get x plus 9 minus 9, which gets me back to x. So that's fine. And it should also work the other way. Of 2x minus 9, which is 2x minus 9 plus 9 over 2. These cancel. Then after these have gone, I can cancel these 2's. I just get x out. Yes. So it works for example 2. And actually this is a much better way of checking it than just using the numbers. So our last part for this video is a little bit more theory. And this part is called the horizontal line test. You can give yourselves a subtitle. And we know that not every function has an inverse. If, for example, we had f of x is equal to x squared, as you all know, that looks like a parabola. And every time you have something on the x-axis, you square it to get your y value out. If we tried to find an inverse function of this, well, we'd then do our same procedure as before. We'd try to get x on its own, which would mean then taking the square root here, and we'd get the inverse function for this as being the square root of x. However, this is not defined for negative x, because we can't take the square root of a negative number. So not defined for x being less than 0. So not a complete inverse, because it doesn't work for the whole domain of f. So we can check this. Just as we checked whether things were functions with vertical line tests, do you remember that because I can always draw a vertical line here, and it only ever crosses the function once, then it is a function, because for every input we need just one output. The horizontal line test says that if a horizontal line crosses the function more than once, the function doesn't have an inverse. So with this function here, if I draw a horizontal line there, it crosses the function here as well as here in 2 points. This means then no inverse according to the horizontal line test. In the next video, I'll be doing a few examples of finding inverse functions and also checking whether inverse functions exist.